Hello and welcome to another video. We're going to be talking about the Powerseries derivative characterization theorem, Theorem 13.11. Now, what is the claim? Standard stuff. Let us have some Powerseries like so. An times x minus x0 raised to n be a Powerseries, right? With the associated, with the finite convergence radius. Now, with the associated convergence radius being finite, and let us call it r and put it greater than 0, then the series, like so, of an times n times x minus x0 is also a power series, clearly. But with a common center and convergence radius, a common with the original series, so with the original power series. Okay, moreover, and this really is the heart of the claim, moreover, the derivative of the sum is equal to the other sum or the other series, right? Now this is amazing. Okay, how do we prove this? Well, the proof is surprisingly not that hard. We shall have it finished in a few minutes. Alright, so we know by the theorem 13.9, I think, that r equal to 1 over the limit superior of the nth derivative of an, the nth root of an is the convergence radius of the original series. Right. We wish to show it is also the convergence radius of the differentiated, in quote marks, series. Okay. The convergence radius of the differentiated series, whatever it is, you can write out the series explicitly. That would be the series where we range through 1 to infinity an times n times x minus x0 n minus 1 is equal to, this is a mere algebraic manipulation, okay? So this is an equivalence operation, because we have that x is not equal to x0, so we're not dividing by 0, so we're fine. Alright. But we know how to compute the convergence radius of this thing, well, rather, of the numerator. So by the, I really think it's Theorem 13.9, we have the radius call it radius prime, equal to 1 over the limit superior of the nth root of n times an, right? But that, of course, is equal to this limit. Again, this is a mere equivalence operation. And this, of course, is just 1 over limit superior of the nth root of an, right? This is because since the limit, and thus the limit superior also, as n approaches infinity, of the nth root of n is 1. But of course this is equal to this, right? So we have r equal to r prime, and thus the two series have the same radius. So, and thus we have proven the first part of the claim, right? Alright, now it remains to show this, the equality, but that won't be so difficult because we essentially have a theorem for this already. So we've already done the hard work, now we just need to apply the tools we already have available. We wish to use Theorem 13.7. That's the theorem which essentially claims that, given some finite differentiable functions, and we are considering a series of functions thereof, and if we have a single point for which this series converges, and if the first derivatives of these functions converge uniformly locally on the given neighborhood, then the function which we put as the output of the series is differentiable, and moreover the first derivative of this function is equal to the series of the first derivatives of the individual functions in the function series, right? And this is precisely what we want to use. So as I said, there are 3 criteria for it. One, that there exists that the derivatives of the functions in the function series are differentiable, which in our case is guaranteed because it is a power series, so it's beautiful and nice and well behaved. We can even explicitly compute the derivative. Now, so we write clearly un equal to an x minus x0 is finite differentiable. Right. Moreover, the power series converges for x equal to x0, because it will be a series of zeros. And we know that the series of the first derivatives of use in this case, but of the functions from the function series, in this case a power series, does converge uniformly locally on on this open ball. This holds by the previous theorem. That was the theorem 13.10. I believe we have it somewhere here. Yeah, right here. Alright, moving on. All the requirements of 13.7 are met, so all the assumptions of the theorem 13.7 are met, and thus if we put capital F of x equal to the power series, then f prime of x is equal to the series of the first derivatives, which in this case is what I'm writing at the moment. No, pardon me. In other words, the derivative of this is this, which is precisely what we wanted to prove. I would just like to point out before we finish that the reason why we require that r is greater than 0, beside other things, is that it is in the requirements of 13.10, right? Otherwise, the uniform local convergence could be broken. It's in the requirements up here. But since we assume that r is greater than 0, the local convergence does occur uniformly on the given interval given by the convergence radius. And now we conclude the proof.